Record and thank you for your patience. I have to install the OBS Studio because this is an old computer. Actually, a new computer that is quite old, but it has VGA plugin, UBS, phone, whatever you want. It also has HDMI. So today I'm talking about block matrices. Uh, most of the many things was already. So I have talked about many things last semester. The big question is that whether it was necessary or not. Did you remember matrix inversion, the methods and everything? So if you saw, then next semester, I mean 1 year later, I will not repeat them. I just continue with the new things because there are many new things. Just I need more time to prepare, and I have to figure out what exercises I will give you. It's not easy. Okay, so sorry for my cool appearance, but my glasses are in my room. Uh, so these are something special. Uh, there are so-called block matrices. The trick is the following. These are big matrices, really big. And it's quite time consuming to calculate them. So the idea is the following. The matrices are divided into parts. And the parts behave like the element of the matrix. And there are smaller matrices, and you can cooperate with them like the elements. Yes. So the block matrices has smaller matrices in the blocks and rows, in the rows and blocks. They have a second name, hypermatrices, but the hypermatrices are different matrices. Sometimes it is very useful if you have multidimensional matrices. Well, you are not computer scientist, but the vectors are the arrays. Two-dimensional arrays are matrices, and sometimes you need three-dimensional arrays. For example, if you have a simulation, any simulation, or then you um, so if you, for example, do a simulation of the interaction of the Earth and the solar wind, then you need a box. Yes, I have unique technique. In this box, you put sphere. This sphere has zero resistivity, unlimited conductivity, and then in this box, in every point of this box, the solar beam enters. And actually you write some system of partial differential equations and you try to fix it. And the fixation and all methods are in cubes, small cubes. And so these are real cubes. And in each element, you do the calculation. Usually, these differential equations are written as some terms of some elements, some multiplication. So there is nothing fancy in them. But in each point, you need the values of, for example, solar density, temperature, pressure, velocity, magnetic field. Because this is in the space, the best, there is, you can store it like coordinates and then the value. But it's much better if you have a three-dimensional array. And this is very valuable. For example, a bow shock, oh, yes, it's here. A bow shock is forming here. And this look like look like this. Now it's understandable why do you need for numerical simulation with computers. Because you have really huge elements, three-dimensional arrays, many of them, and you have to calculate this for each element. Okay, let's calculate. For example, a typical box for my simulations starts at minus 32 RE, it's Earth ready. It goes, no, it's plus, sorry. It goes to the tail, it's 260, and it means it's, okay, it's around and the smallest box is 500, 1,000, 2,000. No. It's 2,000 is the resolution. This and so you have something that 8 billion cubes for the simulation for one data, and there are at least 8 different data, but there are more. So if you can increase the resolution, there are different ways to increase. For example, there are intelligent frames. They find, oh, here is something interesting, and then it increases the solution. But the simplest way to use equal cubes everywhere, and then you need plenty of what is the name, memory and disk and everything else. So these are the hypermatrices. This is not the next, but I will talk about them this today. Okay, you can do the following. You have a differential equation, and not differential equation, sorry. You have a system of linear equation, and the system of linear equation has coefficients. This is the A matrix. The B is the result, and of course the vector x, y, z, z1, z2, z3 doesn't matter. That is somewhere. So you have this matrix, and you have to do operation with this matrix. But this matrix is 5 times 6 its size, and it's difficult to do anything. So what you can do with these lines, you divide it into smaller matrices, blocks. Okay? You can do the operations like normal matrix operations with this. What does it mean? Here, this is a special matrix, and the matrix elements are matrices, and this block matrix can be multiplied by scalar. You do the operations in the same way like in a normal matrix. You also can add this. This comes from the linearity. This is the additivity and the homogeneity of the matrix. The problem comes when you want to multiply these blocks. So, just a moment. If you have the appropriate size of matrices, I mean no matrices. If you have the appropriate size of blocks are matrices, of course. The appropriate size means the number of columns of the first block and the number of rows of the second blocks are the same. You can do the multiplication. And this multiplication is just a matrix multiplication. It was very similar to the elements. Okay, now the tough part. Some calculation. It's not easy. It's easy to miss. It's very good for a test because then you cannot use any computer. Okay, let's see. We have two matrices. These are small matrices. Of course, you can do the calculation without blocks or anything. But here, can you open the window, please? That I have opened one, but you can't. Well, you should be strong woman and turn it anti-clockwise. No, I'm joking. No, don't do it. Don't do it. Don't take it. I have a job interview with someone. I would like to hire a PhD student, and she told me she's a strong woman. Well, we will see. The stipendium Humbericum is very tough. Do you have stipendium Humbericum? Okay, she's applying for that one. Well, there are some funny parts, but we will see. Okay. Actually, this is sad. When you apply, you don't. Oh no, you are yes. Then you not a problem. Okay. Uh, I got many emails for stipendium Humbericum applicants everywhere from the world. They're applying for PhD. And usually they are wondering because they send 50 emails to Hungary and I'm the only one who are answering. And it's a bit interesting because we need PhD students. I need to be a full professor to have at least one. In an American university, you have 2 per year PhD students. So there is big difference. My supervisor is retired, my former supervisor, and he has 2 PhD students in his whole life. There are big differences in different universities. Okay, doesn't matter. So, thank you for opening the window, and let's return to this block stuff. Actually, it's very interesting. So this is only for the demonstration. You consider all elements as different matrices. You know the vectors, and sometimes the scalars are also matrices. What is the first element? You take, it's very funny, and I would need a pointer, and I haven't fixed my pointer yet. Actually, I tried it. Doesn't matter. I'm moving somewhere next weekend, somewhere else. So there is this 1, 0, and that's an element, okay? And what do you do with the matrix? You multiply. That's funny. I always tell that you multiply the rows and the first row of the first matrix and the first column of the second matrix. But that is a shorter description. It means each element is the scalar product of the appropriate row of the first matrix and the appropriate column of the second matrix. That's true, just I never said this. So the first element here is the 1, 0. The second element, this is the first element of the first row of the first matrix, and then the first element of the first column of the second matrix is this 1, 1. So 1, 0 times 1, 1, nice. You add the second element of the first matrix, of the first row of the first matrix, and multiply with the second element of the first column of the second matrix. This is the first element of this block matrix, and then you do the same for each. I would need a pointer, or perhaps on the computer I can put. So this is the first element of the first matrix. You multiply with the second element of the second matrix in the first no, the first element, oh, doesn't matter, you know where is it. So you do the same like with the normal matrix. Then you add this element and this element. I mean the multiplication of that one. We will do this tomorrow, and perhaps if I will have time today. Uh, it's actually it's easy. Just then this one is multiplied by this one. It's like a, can you see? It's like a matrix calculation. It's exactly the same. And then you add this one, multiply this one. Then the next element, this element is multiplied by this element, and this element is multiplied by this element. If you do these lovely matrix calculations, you got these elements, and then you just leave the brackets, and then you have the result. Actually, you can calculate this is the right result here. We don't learn algorithms, but it could be easier to calculate in this way and faster. It has also has a, what is it, a special knowledge how to find the size of the block matrices. Okay, can I? Can? Okay. Oh, there are interesting things. There are always something new. We derived some, not some, all of operations were derived from elemental matrix operations. Multiplying scalars, multiplying elements, adding together elements. This is something special, this VEC function. I hope this VEC function is also in English. I didn't check whether this VEC function is in English, but based on the definition, you can understand this. It's very simple. You have a matrix, and you made a vector from the elements of the matrix. For example, if you have this 1, 2, 3, 4, then you then you transform for this vector. It means from each row are put in one column. So this is this operation, but this is only the beginning. This is only the beginning because now something new. Two matrices could have so-called Kronecker product. Well, only a name like Kronecker delta. It's also it has another name. It's called tensor product. You have two matrices the size of m times n, and another matrix p times q, and the new matrix size will be m times p times n times q. So what does it mean? We have these two small matrices, and you take the second matrix like a block here, And you can see this is the second matrix just multiplied by -1. This is the second matrix multiplied by 2, 0, that's easy, and it's the second matrix. This is a new operation. It's the Kronecker product, and this is the O times, that means in LaTeX, uh, that's the name of the operation. And for each matrix, you just take the second matrix and multiply the elements of the A. So just you can see, take the second matrix and multiply each element of the first matrix, and you got this huge matrix. Problem is that I cannot tell you any example where you can use this in this moment. I never use this, but you must know it, or at least the physics students should know it, because it is in the syllabus. Now I'm merging things. The Hungarians and the English classes has different topics in the syllabus, and I merge them. It has a very simple reason. I don't want to prepare for two talks, only one. Even this one is very exhausting. Okay? Okay. If you have an operation, the operation has different features. So if you have these matrices must be selected very carefully, because of the size, but doesn't matter. So the size of the A and B are the same. The others are not so important. First of all, this is distributive, this operation. A matrix plus B matrix O product, Kronecker product C matrix can be shared, distributed in this way, just calculating the first and the second. And this is true for both sides. Then it's associative. If you have an ACD matrix, then you can change the brackets. So you can move the brackets. If you have a transponent and you will meet the the extension of transponent in this lesson very soon. Not here, but very soon. Then you can do the following. The Kronecker product of A and C, you do the transponents, and it's the same like the transponent of C, transponent of A, and you apply this Kronecker product. That was the same for the matrix multiplication and transponents. And I taught this last semester. We didn't use it for anything, and this semester I use it in a deduction. Okay, great. I will modify a little bit this text later. So by definition you can prove all of these, but we won't. No. Okay. hypermatrices, I just gave an example when you can use these hypermatrices. These are not the block matrices, these are something different. First of all, this definition is for multidimensional or multidimensional space. When I talk about S set, that could be the set of or the body actually, body of real numbers, rational numbers, or integer numbers, or natural numbers, doesn't matter. The definition of this d-dimensional or d-order hypermatrix is the following. You have this n1, n2, blah, 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 and d. These are the numbers of the elements in rows, columns, other columns, hypercolumns. I don't know what is their name. You have elements in each row, and you do the relation for an S, for the elements of an S set. That could be any number. And this matrix can be written in this form, and this means nothing, just this is an element. It has many indexes, and if you go down and just write it in 2-dimension, you get the same that you had at matrices, 2-dimensional matrices. If all dimension has the same number of elements, then we are talking about hypercube matrix. That's an interesting stuff. Actually, I can't imagine in this moment how can you use more than 3-dimensional matrices. When you are filming the Interstellar and you are in a black hole and you have space-time, I mean space, 3-dimension, 1-dimension. Oh yes, okay, I have examples, but it's physics. Yeah, in general and special relativity theory, you have free space and one time dimension. But there is a very special coordinate system in classical physics. It's called phase space. Have you ever heard about phase space? Have you studied quantum mechanics? No. But you will. It's not in the curriculum. Really? Quantum chemistry is not just separate. Not quantum chemistry, just quantum mechanics. Not in quantum. Not in quantum? We don't have physics after the first year. Did you learn theoretical physics mechanics? Mechanics? We just did basic mechanics. Basic mechanics. Yeah, it's very basic. You never heard about Lagrange mechanic and just a moment. Not Lagrange. What was the other mechanic? You never heard about Lagrange mechanic? No, doesn't matter. So there is a special coordinate system. It's called phase space. then you have three dimension for the coordinates, and instead of space or anything, you have the impulse. Three-dimensional impulse, three-dimensional space, and then you do anything in a six-dimensional space. Doesn't matter. That's just an example for these data structures. Actually, perhaps from industry, I should give you about the BUX index or NASDA index or something like this in stocks market or something like this. But sorry, I'm a physicist, so I can give you this example. Okay. The elements of these hypermatrices are just this one. This is nothing more just in the indexes. I will give you an example tomorrow. If you go back to second order, I mean two dimension, that's just a matrix, nothing more. However, you have problems. Problem is the following. You have a three-dimensional matrix, you have a paper, and you have to do operations with it. That's funny. Now I feel a little bit in a Stone Age because this part is for perhaps for students or something like this because you never do this with a three-dimensional matrix. You have hypermatrix with size 2 times 4 times 2, 3. And if you look in the indexes, then here this is not really a block matrix, but the free matrix in space in Z component is written not, I don't know, it's like my cube on the board, but in a plane. So you can exactly see the row, the indexes of the row. It's the first, then the second is the column, and the third is not the column, but it's in space. You write this in this way. You can do the same with the hypermatrices. Just you have to write much more indexes. You can do the addition like in block matrices or matrices. Do you recognize it? This is an element of hypermatrix. It has different indexes, 1, 2, 3, whatever. It's a different element, and you can add together. It's like matrices. It's the same. Just here you don't have this A11 and plus B11, but you have E1, 2, 3, 4, 5, 6, 7, and then B1, 2, 3, 4, 5, 6, 7, or something like this. It's great to confuse and destroy full query systems and anything. You ask about, not you, he's not here, you ask about why I use Linux last week. The operation system has different definition. One is to protect the resources. It's a multitask and multi-user system. Therefore, this Windows is not an operating system because it's not multi-user. What does it mean? If there is a program, a process, the process is a program with the reserved memory. You know Neumann principle? John von Neumann? He was originally a chemist. and then he switched to mathematics. He learned first in Hungary, studied, and then he moved to Germany. And he was a very, very good mathematician. The Neumann principle says we do not separate the data and the programs in the computers. They are together in the same memory. There are different principles. You could store the program and the data in different way. That's why there is not so much difference between the DVD, that's writable and rewritable, the memory, and the CPU memory. The CPU has a very fast memory. It's very expensive. That is and very, very, very small because it's expensive. And so, if you do a calculation like this, then you reserve memory. I mean, lot of memory, terabytes. I mean the memory, not gigabytes in the memory, terabytes. And then if there is any problem in the operating system, then everything breaks. The operating system must protect the memory. You can do it in Cray, then you got so-called segmentation fault, and then for a few minutes the memory is written, some terabytes are written in the disk. And also in the old days you could meet with it at Windows, that's the blue dead. When there is a program and then other program reaches the memory of the first program, then it's not allowed, then core down. And when it's a critical system like Windows, then it fails. In Unix, Linux, everything, so the keyboard, the screen, the internet, if you have web server, anything, are a process, and any of them could break, and then you just log in and restart. There is only one exception, the kernel, that's the memory. If that memory breaks, then everything collapses, but that's rare. So Unix systems could run for years. Here, these are the elements of a hypermatrix. It has any dimension, 100 dimension, 100 index. You never write this down. And this is the additivity. And you can do the calculation with just a scalar. That's not multidimensional, just a normal number, like real number or something like this. And you have this, it's allowed for that operation. Now, transpose of a hypermatrix. Instead of T, we use P. Actually, we should use zeta, something like this. It's quite easy to write P. I'm just kidding. This is a generalization of the transpose. So P should be a permutation of the set of these numbers. The transpose of higher order hypermatrix E is this. And what this means? This is a permutation, and these indexes are permutation of the original elements. There is another definition for symmetry. You have a hypermatrix. You do this operation, and you got this. And if you got the same matrix, then the matrix is symmetric. If you got not this one, but that's funny, -1, then it's Q symmetric. But here, this is not a minus. It is a special function for one direction of the permutation. It's -1. From other direction, it's 1. Okay, no one understand? So we can continue. Okay, here we have these hypermatrices, and this is a 2 times 2 hypermatrix. I'm very happy that I don't need to give you a 5 times 5 or 4 times 4 times 4 times 4 hypermatrix. Doesn't matter. This 2 times 2 hypermatrices. The symmetric matrix is that one. This is quite interesting because remember the symmetry. Symmetry means for a normal matrix, it's symmetric for the main diagonal. But now we are in space. So, zero space. That's a very weird object. Okay, next one. We will take a look for this tomorrow. For 3 times 3 hypermatrices, This is general form. Uh-oh. Something is bad. Very bad. Sorry, this is the Hungarian stuff, and now I started with the Hungarian. Last semester I always started with the English. Yes, this is missing from the English. So this is a 3 times 3 matrix. Uh, and the first is a symmetric hypermatrix, and the other is a skew symmetric. And perhaps there is a mistake in it. No. Oh, I know there is something perhaps, but it's in the code. Now, because it's not my computer, I cannot correct it. I will. Okay, let's check this. So this is so A, B, C, D, D, E, C, E, E, B, D, E, D, G, H, then C, E, F, E, H, I, F, I, G. Uh, okay, I give it that. So I cannot imagine this. That's the antisymmetric or skew symmetric matrices. Perhaps it's easier. So everywhere it is 0. Here I have E. Here I have minus A. Then, no. This is A. This is minus A. Then this is A. This is here minus A, and then A, and then minus A. Okay, at least here I see something that is symmetric for the center of the cube, but I don't see anything on that, and it's difficult to interpret that one too. I mean, the 2 times 2. I have the feeling that uh, this subject is for the physicist mostly. You don't do calculations or anything.
Yes, we have put the calculation matrices.
Linear equations? Reaction equations?
Yes, but I guess not.
Do you solve a system of linear equations?
We haven't had to, not in lab or in our math classes, but not in any of our chemistry courses yet. Maybe we will.
Was this one linear equations in the seminars? We were solving problems?
Yes, the inorganic.
Yeah.
I'm trying to remember.
Okay. Thank you very much. Class dismissed. And tomorrow I will give you examples for this. And also, last time I mostly talked, so the examples are for that one. And I have to figure out what to ask you in the test. Okay. Thank you very much. Thank you. Have a nice day too. Thank you. See you.